State, but the whole department was very impressed by her. So we actually decided that she deserved to graduate with distinction from our program. She's been doing. Take it away, Jen.
All right, thank you. So hi everyone, my name is Ortiz, and the research I did over the summer at Lawrence Livermore and throughout my senior year is titled Pole Shape Discrimination, Analysis of the Time Projection Chamber Vacuum Detectors. My mentors is Dr. Teal Pershing of Lawrence Livermore National Laboratory and Dr. Alexandra Miller from Sonoma State. So a little background on motivation is dark matter searches. For those of you who does not know what dark matter is, it is a form of matter that does not emit, absorb, or reflect light, making it invisible, but its presence is primarily detected through its gravitational effects on matter, visible matter specifically. So getting into the pie chart here on the upper right, it shows the energy distribution of the universe made from the Sean Jackson Observatory, and it shows the distribution divided into 3 different parts, with dark matter being about 26%, which is actually a lot if you think about the vastness of the universe. And then here it shows a model of the Milky Way with a dark matter halo far exceeding it. And that's the case for all galaxies. Dark matter makes up about 70 to 95% of the total mass of all galaxies. So since it plays a crucial role in the universe, we want to know what it is, but it's dark, and so we have no idea. And so it leads us to a lot of diverse dark matter searches. I'll state a couple here: gravitational lensing, cosmological mapping, acceleration and laser-based searches, and direct detection experiments like Lux Zeppelin. And this is what I was mostly doing research under, direct detection experiments. And so WIMPS is a candidate under that direct detection experiment. It's one of the candidates. It stands for a weakly interacting massive particle, and it has all the properties a dark matter particle can have. How we search for this is through a detector called a time projection chamber. And these time projection chambers were created because theoretical physicists suggested that a WIMP can recoil off of high atomic nuclei. An example of this is xenon, argon, and neon. And for example, I'll just, for this example here, I'll just I'll use xenon. So here's 80%, let's say it's 80% of the liquid xenon phase and 20% of the gas xenon phase. And so a WIMP particle will come in and recoil off of a xenon nucleus, and it creates 2 types of signals, charge and light, and is detected by the top and bottom photomultiplier tubes here, or how we detect all of it, basically. And so there is a backup experiment called the dual phase xenon neutron, or XENU, time projection chamber, which doesn't directly look for WIMPs, but it does use neutrons to simulate WIMPs, because neutrons also recoil off of nuclei, high atomic nuclei. And so this is a diagram I created here, where it's a neutron generator that generates neutrons, and they come in at a certain angle, also will recoil off of the xenon nucleus inside the time projection chamber. It can escape, hopefully, and hopefully get caught by one of these vacuum detectors around here that's also sensitive to the recoil. And so they're placed at known angles here. So since we know the incoming and outgoing angles, we can then calculate the energy values, highest and lowest. And so then we can know, if we're actively looking for WIMPs, we can know which type of energy, or which energy values to look for. And so that's basically one of the main contributions the Xena TPC does for WIMP experiments. And so my main research, I didn't directly focus on the time projection chamber. I mostly focused on the vacuum detectors, and this is what it looks like. So there's that diagram I had on the last slide, but this is the real life version with the time projection chamber right there, and then the vacuum detectors all around it. And so in each of these vacuum detectors, it has this, and it's a liquid scintillator that is sensitive to recoils as well, but it also converts particles to visible light. So like, let's say a high energy photon comes in, it'll convert that to visible light here. That's the liquid scintillator. Then the photomultiplier tube converts that to a photoelectron, and then it accelerates it through the electric field and amplifies it through diodes, and it comes out as waveforms. So basically what I collected was a bunch of waveforms, which leads me to my main research question, which was how well can the liquid scintillator vacuum detector discriminate between neutron nuclear recoils and gamma ray electron recoils. To do this, we use 2 sources, and they both are do radioactive decay, hence my Imagine Dragon reference, because they have a song in this album called Radioactive. Californian's the first one, which emits neutrons 3% of the 3% of the time through spontaneous fission, and gamma rays 97% of the time through alpha decay, which is an emission of a helium nucleus. Cesium-137 emits only gamma rays through beta decay, and so we use both of these sources. We mainly focused on the Californian because it emitted both of these particles. And so basically what we did was we put it next to the vacuum detector, and it'll go in and recoil off of the silico scintillator, and then we cache that. And then, but the main thing is the waveforms we collect are different between the nuclear recoils and the electron recoils from both these particles, which I'll get into here. So yeah, starting off with neutrons, they do a nuclear recoil, so that means they recoil off of a nucleus, and so they give energy to the nucleus, and then the nucleus goes off at some angle theta with some momentum and velocity, and then the neutron will go off at some angle phi. And since it's excited, it's gonna. So something I should say first is that it's heavy and it moves slowly, but it's excited as well from after interacting with the neutron. So if it's heavy and slow, it's going to it leads to a high linear energy transfer, which creates a dense group of excitations, ionizations, and free electrons, which leads to things combining into these things called excimers, specifically triple state excimers, which emit light more slowly. Like they emit light, or how do I say, de-excite more slowly, which comes out. So when we collect the nuclear recoils as waveforms, that causes the specifically the tail portion of the waveforms to come out more spread out and decays more slowly, and have their amplitude higher as well. So getting into electron recoils, it's the same exact process, except the gamma ray recoils off the electron instead of the nucleus. And so it's the same thing, except an electron's smaller and lighter, so it moves through faster and excites things in a far distance. And so it leads to these excimer states that are single excimers instead of triple state excimers that then emit light more fast instead of like a slower decay time, or slower light emission, I should say, or de-excitation. And so it causes the tail to be more prompt here, like in having an overall like less area. And so that's the main difference. The tail portion is the main source of how we can discriminate between nuclear recoils and electron recoils, and how we compute pole-shape discrimination. So these are, so I got about 90,000 waveforms for each of the sources. So this is just a 2 for the Californium, just 2 random waves. I just wanted to show how I calculated it. So the tail portion was the main thing, right? So I took this window and divided it by the total energy. So this is just the energy after that peak, that main source of pole-shape discrimination divided by the total. I did that for all the waveforms, and then I plotted it. So yeah, just physical meanings. Q tail is this window here, which is the total energy after the peak of the waveform, and then the Q total is the total energy of the waveform both before and after the peak. So that's how you calculate pole-shape discrimination, how you can know what is neutrons, what is gamma rays. So I plotted it here. So this is the pole-shape discrimination versus the total energy. And you can clearly see 2 populations of the Californium. Something to note here is there's baseline noise at the y-axis, just because it's just baseline noise. Like it's like other things that's not important. But then once you get to an ADC count energy value at about 5,000, you can see the discrimination happening with neutrons overall having a higher pole-shape discrimination. And something to note too is that neutrons, we got less data for neutrons, and this is because Californium emits neutrons 3% of the time versus gamma rays 97% of the time. Second thing is because of that dense, because nuclear recoils create a dense area with all these excitations, ionizations, and free electrons together, it creates this thing called quenching, where energy could be lost to something other than light, like heat, for example, instead of light. So we lose light, we don't collect that from the photomultiplier tube. And so yeah, 2 populations, really nice. This is our test data cesium, which only emitted gamma rays. So yeah, that just kind of confirmed for us, like, we know it's gamma rays, right? And I also did an additional PSD analysis where I did another plot of, I did the integral of all the waveforms for California, and I plotted it versus their peak amplitude. And yes, neutrons overall have a higher peak amplitude integral because of that tail is more spread out. And we see 2 populations here as well, which is a good thing, because like we get to know what particles what. And yeah, so I got a success in finding a good pole-shape discrimination in the neutron and gamma ray waveforms, and this is good because it improves particle identification, reduces background, and enables more accurate event reconstruction. It's for like bigger experiments. And if a WIMP had a book, it would be Divergent would be particle, because it matches the names. Like, come on. And some acknowledgements. So I want to first off thank Dr. Alexandra Miller and also Dr. Wintu for as supporters and lead mentors of the Growth NSI program. Also Dr. Teal Pershing and Dr. Jin Kizu for supporting me and like helping me learn so much, especially in coding throughout my research. Also some grad students who also got their PhDs this year that worked at Lawrence Livermore congratulations to them. But yeah, no, they helped me a lot, because there was a lot of things I was lost on, and like I learned so much from them, especially on hardware and stuff, so I'm very thankful for that. Also the McNair Scholars Program for guiding me through the writing research process, and also, of course, the Department of Energy, because of the funding. Alright. But that's it, yeah. Oh wait, there we go. Thank you guys.